All right. Let's see. Okay, so before we get going, does anyone have any logistical questions? Uh, I don't know, personal questions, whatever you want to ask. Yeah, I'm happy to talk about anything related to or not related to the course. But okay, sounds good. I think y'all have had a bit of a break. I believe the spec for Project 2 came out last night. And I'll talk a little bit about that at the end and just um, tell you sort of like how I approach the project. And then hopefully it'll make it a bit easier for you all to like conceptualize how you can do things. But we will see. All right. So if no one has any questions, let's get going. It's September 28th. We're talking about priority queues. Y'all have already done priority queues in class, right? Can you either click yes or say yes? Yeah, okay, great. Just wanted to make sure I wasn't doing, I used to teach this lab that it was Monday mornings and it would always be before lecture and we'd be lecturing on like the things that the lecturers were going to lecture on that week. It was terrible. So I was always teaching everything. Okay, so here's some logistical things. This slide is more for you than it is for me. So I'm going to keep going, but if you feel inclined, come back, check it out. It's got some important dates. All right, we'll talk well, yeah. Does anyone want to talk about the Lab 3 handwritten solution? We can go over it if you want. If no one wants to, then we'll skip it. Okay, we'll talk about it just briefly, just go over our solution, talk about priority queues, heaps and heapsort, sets, and then there's another handwritten problem. So from last week, we want to check if two strings are anagrams, and we get to assume that the strings only contain lowercase letters and spaces. So like one solution is basically like you can just have a vector of size 26, and that counts all of the occurrences of each letter in the word. So like, for example, in Apple, the index at 0, which corresponds to A, would have a 1 in it, and the index that corresponds to P would have 2 in it. The index that corresponds to L would have 1, and E would have 1. So this is trying to just make a point that, like, in general, there are other characters, but I would say for now, don't worry about it. Okay. So here's an implementation of it. Basically, like the important thing here is this is how you get the index for a lowercase letter. Same thing here. And then we're just doing, plus or minus based on what we see. So the first string will add, the second string will subtract, and then we're going to just see if they're all of the entries in the vector are 0. If they are, that means there were exactly the same number of letters, or exactly the same counts of each letter. Strange thing to say, in each word, which means they're anagrams. Okay, let's keep going. Oh, does anyone have any questions about this? Just click no or yes maybe in like the participants thing. Nope. Okay, we're gonna keep going. Priority queues. So priority queues are hugely important in project 2. There's two parts of project 2. The first part is just using priority queues, and the second part is implementing priority queues. So altogether, you know, it's probably like half the grade of the project is just dealing with priority queues. So very important. A lot of times, you know, we think about as a programmer that has worked in various parts of the industry and academic research, we think about priority queues a lot because there's a lot of times that we're interested in serving requests based on some information we have. So actually, we think about this quite a bit in terms of the office hours queue. We talk a lot about, you know, would it be better if we had a priority queue for the office hours queue that, you know, basically picked the students to be first that hadn't been helped that day or something. And obviously there's, I mean, you know, that's a whole other conversation that we on staff are talking about, but just to use this example as a point that we think about priority queues quite a bit, and they're actually hugely important. So it's a good thing to know. That's why we're doing it. Okay, so it's an ADT. You can put something in and you can take something out, and whatever you take out is guaranteed to be the highest priority of the queue. So there's a number of possible implementations of this, several of which you will go over in the project, but really there's like a ton of different ways to do this. One of the ones that you'll be going over in the project is like the accepted standard for priority queues, so binary heap. Okay, so this is the STL priority queue interface. Push, pop, top, empty, size, right? So we can read things off of the queue, we can remove things from the queue, we can push things onto the queue, and then we can tell if it's empty and how many items are in it. We can't iterate over it. We have no idea what the order is, and it doesn't matter. But I do see quite a bit that people will try to iterate over their priority queue in project 2, and that is not something you need to do or want to do. Don't worry about it. Okay. Here is the templating for the priority queue. It's a little confusing. Basically, the first argument is the type that you're putting in it. So I don't know, say we're working with students and we're interested in, I don't know, what would we be interested in? We're interested in helping students with low grades. So the student has like a GPA float or double in the struct. And so the templating would look something like, you know, we have student, name. I'm just gonna pseudocode this, I guess. String name, and they have a double, which will be GPA. Okay. And then our priority queue will be, the way we'll do this would be priority queue. And then you have your type. You have the container, and the container is just specifying what underlying data structure you're going to be using to implement a priority queue. So if you choose vector of student, then you'll be using a binary heap, which you'll implement in project 2. So you'll learn more about that soon. And then the third argument is the comparator. So obviously, just less than wouldn't work here because student doesn't have less than defined on it. But there's a few different ways to do this. One way you can do is a lambda student, oh God, call that an ampersand. How do I haven't even tried to draw this anymore. Ampersand. We're trying to reference a student 1 and student 2. And we're just going to return 1.GPA less than, oh man, this is getting kind of shitty in here. I'm sorry. I'm just going to do it right here. 1.GPA is less than 2.GPA. Okay. And we'll close that off and we'll do that. Okay, so that's a description of how you can instantiate a priority queue. That got really messy, and I'm sorry. In the project, you'll use comparators, which means you'll be like writing classes, and they'll have overrides of the parentheses operator. Or you can use lambdas. Usually, a lambda is like something you want to do if you have like a single line. But your comparators for the project will be more complicated than that, so you'll be using multiple lines. Okay. All right, great. If you want to override the comparison operator, you also have to set the container type, right? So you can't just say like int, basically it's saying like you can't do this, right? You have to provide that middle argument. And the reason why I'm telling you all this is because sometimes priority queues come up on the exam, and you have to know how to instantiate the priority queue on the exam, or else you'll lose points. Obviously, when you're just working on your code, you'll figure it out. The IDE will tell you that you're doing something wrong, but you need to know how to do this for the exam. Priority queues are almost always one of the written questions. Okay. All right. Any questions on instantiating priority queues, conceptually what they're doing, why we want them? What all this crazy scribbling I did was. All right.
Sorry, quick thing.
Yeah.
The whole compare and when the comparator and the vector in the template there's like it puts in the T already. Do you need to specify that yourself, or how does that work?
In the template, it puts in the T. Are you talking about the class compare equals or class container equals?
It's off. Container, for example.
Yeah, so you have to describe that. For example, here at the bottom of the slide, we need to say it's a vector of ints. Yeah, you're gonna have to say what the type is throughout the declaration.
Okay.
Does that make sense?
Yeah.
Okay. Yeah, it's not, I mean, you would think that like, well, we should be able to infer, or the data structure should be able to infer if I pass it the type initially, then it should be able to infer like what the type of the container is going to be. But I believe the way that they do this is that they're just going to use container as a constructor in the implementation of the priority queue. So they don't actually, they can't template the type inside of the construction of the container. So it's important that you provide the type. Yeah, okay. Great. We will move on. Okay. Oh, yeah, I forgot my mouse shows up on the screen, sorry. Find the kth largest element in an unsorted vector. All right, someone doesn't have to be right, doesn't have to be efficient. Someone tell me what is an idea that you have for doing this? Just like the first thing that pops into your mind. I have an unsorted vector. I want to find the kth largest element in it. Doesn't even have to do anything with priority queues. Nobody has any ideas.
Sort them first.
Okay, so Sam, I think you said sort it and then just index in at k, and then we have kth largest, right?
Mhm.
Okay.
Oh.
Yeah, I mean, perfect, right? That'll do it. That'll give us the correct solution every time. We just sort the vector and we find the kth largest element. Okay. Can anyone tell me what time complexity that's going to be?
N log n.
Yeah, and log n. So sort, then index, right? Indexing is a constant time operation. So the bulk of our time here is taken up by sorting, which is an n log n operation. Okay, so we can do it in n log n. Great. Can we do it any faster? And also, I mean, the slide says priority queue at the top, so maybe now we can think about ways to use a priority queue in this implementation. Okay, so what is one way that you could use a priority queue here to find the kth largest element?
I mean, you create a priority queue and then you just pop until you find it.
Yeah. So let's so insert all n elements into a priority queue. Pop k minus 1. Top is the k largest. And this is assuming that we have a max heap priority queue, right? So that the max is on top. Okay. Okay. What is the complexity of this? Let's just start with the first part. What's the complexity of insert all n elements into the priority queue?
Is that n? Log n? N log n?
And log in. Yep. Okay. Oh, n log n. And actually, we'll talk a little bit about like you can use heapify, and then this can actually, we can call this O of n. If we are smart. And then boop, pop k minus 1 elements. What is the what's the complexity of that?
I mean k.
Okay, so it's k. We're popping k elements, but every time we pop an element, what has to happen? We have to restructure the heap, right? Okay, maybe y'all aren't super familiar with this. This operation is going to be k log n, because for each of k operations, you're going to be doing log n work to restructure the heap after the pop. Okay, so this is one good solution. I think this looks pretty reasonable. I think, yeah. Okay, so then we'll get a little bit better in a second here. Okay, n plus k. Oh yeah, okay, my bad. This is n plus k. Yeah. Okay, so this is what we have here, right? We have our first operation is n, and then we have plus k log n. Okay, so that's pretty good. If you don't use like the range-based constructor, like heapify, then this becomes O of n log n because because basically this part can be O of n log n if all you do is push elements in until all your elements are in there. So that can be a problem. N plus k log n. So, okay, that's where we're at. We have n log n in the worst case, n plus k log n if we're smart. Okay, now we can do approach number 2, which is we only add k elements to the heap in the first place, and then we just push and pop each of the remaining n minus k elements, right? So let's say n is 10 and k is 3. You'd add k elements to a heap, and it's important that this is a min heap because we're not interested in keeping around the minimum element. We want to cycle it in and out. So we're going to push we're going to push our 3 elements into the heap, and then we're going to push the remaining 7 elements and then popping out each time. So the size of the priority queue will stay as 3, and then what am I trying to say? The size of the priority queue will stay as 3, so then we're just dealing with log k there instead of log n, which is what we want. Yeah, so this can be a bit better. And then at the end, the minimum element is the kth largest element in the unordered vector, and so we're done. So this is O of n log k and O of k space. So you kind of have to like think about whether, in your problem, is k or n going to be larger? Well, I mean, k is not going to be, but is k going to approach n, or is k going to stay very small, basically? And then based on that, you can choose whether you want to use this or that. And also, obviously, like the space is important sometimes. If the space is important to you, then you have to think about that as well. Okay. Okay. Any questions on either of these implementations of this problem? Why we even care about this? What we're doing? Okay. If no one has any questions, we will move on. We're going to talk about heaps and heap sort. So binary heap is one of the ways to implement a priority queue, which you will do in project 2, as I keep saying. And heap sort is sort of like an algorithm that falls out of having a heap. So a max binary heap is a binary tree where each node has an equal or higher priority than the priority of all of its children. So if we have, ooh, I'll do it with the, this is fun. And then it'll have children, and then there'll be children of those. Is this a cool color? Okay. So we have our tree, and we have our nodes, and we know that on each level, the root node of that subtree will be the highest priority in that tree. But that does not mean that we have any conception of what the lateral relationship is between these nodes. So these two blue nodes there's no relationship between them besides that their priority is both less than the green node. Does that make sense? This is all, I mean, this is what a heap is, right? So I'm just describing the definition of this thing. Okay, and it's complete because we want to represent it a certain way in memory. So what that means is that this is not possible. We can't have a missing node on the left of the tree when there are nodes on the right of the tree. How that would work would be if there was a node removed, it would have to be this one. So the tree always fills in left to right, and you'll see why. Well, I think you've seen why in lecture, and we'll talk about why in a second. So let's just talk about a little practice. Which of the following represents a min heap, a max heap, and we'll just do them all and we'll decide what is what. Okay, so I'm gonna do the first one and then y'all will do the rest. So for A, I'm gonna just draw out the tree, and then you'll tell me whether it's a min heap or max heap. Okay, so 1 is the root, 8, 4, 9, 12, 11, 7. Okay, you see how I did that? I just like filled the tree up, starting from the left, going to the right. Once the level was full, then I move down a level, start filling again, left from right. Okay, is this a min heap, max heap, or neither? Anybody?
It's a min heap.
It's a min heap. Yes, it is a min heap, because we can notice that for every subtree, and I will highlight the trees. So here's one tree, right? And then here's another tree. Here's another tree. And then the leaf nodes are a trivial case, but for each of these subtrees, the root node of the subtree is the highest priority, which means in this case it is the least, as like integer comparison. Okay. All right, so this is a min heap. Can y'all just take a minute and, wow, that was really atrocious. Do the next 3 and then just post in the chat when you're done. Or not when you're done, but post answers when you get them. All right, are y'all working on this, or do you want a little more time? Okay. Just do a little more time. Okay, I'll start on B, and as you all finish up, to start posting your answers. Okay. Oh. All right. Okay. So for B, 3, 4, 5, 7, 12, 11, 8, 6. Okay. This just broke the constraint. Okay. Julia says B is neither, C and D are maxims. Okay, so we'll do them all together. Anyways, but I'm glad that you all tried it. Okay, so I'm seeing that right here, my constraint is being broken because of this relationship. So I can just be done with this one. I know that this is not a valid heap. Easy. Okay. Either. All right. Sort of screwing myself with space here. Man. Neither. Okay. 13, 10, 6, 8, 7, 4, 2, 5, 1, -1, 0. Okay, no problems there. I think that's a max heap. I think y'all concur, so we're good. Okay. And finally, -1, -9, -3, -10, -11, -5, -7, -12, -13. Okay, so that's a max heap. Right, so the point of going through this is just to show you all that it's really easy to construct and verify a heap from the array representation. So I'm glad you all did that, and we've done it together, and we're going to move on. Okay, we did it right. Nice job, everybody. Okay, so like we've been doing, we think of the binary heap as a tree, and then in code, in memory, the trees are actually arrays. And we can do that only because we, well, not only because, but we can do that efficiently only because the tree is guaranteed to be complete, right? So we could imagine if we could have children coming off this side, let's say 0, then our array would look something like, we'd have 1, 2, 3, 4, 5 empty spots. So 0, 0, 0, 0, 0, and then our actual 0, which doesn't make a whole lot of sense, right? Because like, what would these spot? Like, what's the default value when it's empty? Like, there's a whole bunch of questions there that would need to be asked, and now we're wasting all this memory. So that's why we have a complete tree. Yep. Thought I had something more to say there, but I did not. Sorry. Okay. Okay, so at position I in the array, what is the index of i's parent? So this is going to be this like little equation, the two equations we write right now are going to be used directly on project 2 in your implementation of binary heap, so beneficial to pay attention. Okay, so I like to just mark things with indices so that I make sure I know what's going on. 5, 6, 7, 8. And then this is 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay. So let's find the index of i's parent. Okay, so let's say I'm at 8. I'm interested in finding 3, right? So let's see. How can we think about this? I think, is it easier to go? I almost think it's easier to do the children first, but I thought these were indexed beginning at 1. So there's a few different ways to look at it. You know, obviously in code, there's going to be something at the 0 index, but whether you fill that with a like a false value or like a sentinel value or something, or whether you actually begin the array at 0 is only a difference of having to add 1, if that makes sense. But I actually do think the math on these slides is indexed at 1. I guess we could do it that way. Yeah, I guess if the slides are that way, then we should do it that way. Okay, fair enough. Yeah, basically, like you're gonna have to do something on the project that accounts for that. And so one way to do that is to just start at 0. And I was thinking that maybe we'd go over that, but we can do this. 4, 5, 6, 7, 9. Okay, so the index of i's parent, let's say we're at node index 9. So I equals 9. Parent of I, or I guess of 9, is 4. So, you know, I guess I would say, like, how do I get from 9 to 4 in computer language? By doing integer division, right? So 9 over 2 is 4. And let's just check that that works for all of these. So 2 over 2 is 1. Great. 3 over 2 is 1.5. The floor of that, which is also, you know, int floor, it's all the same. Is also 1, so that checks out. Let's see, 4 divided by 2, 2. 5 divided by 2, take the floor, it's also 2, right? So it seems like this is going to work out for us. Okay, what are the indices of i's 2 children? All right, so if we have, let's say I is 1, then on the left side we have 2i, and on the right side we have 2i plus 1, right? So it's a pretty simple relationship between the two. And to take that to 0 indexing, not difficult. You just have to add 1 in a couple places. So, okay. Here's the, okay, so this is actually in 0 indexing, right? So this is if this is the case. Some nice IA must have changed these slides because usually we don't do that. But yeah, so this is the 0 indexing case. You just subtract 1 from I and then divide it by 2 to get the index of the parent. And then I believe it should be this. It should definitely be that. And then the index of I's two children are just, you just add one to what we found here, right? So add one to that, add one to this, and then you get the two children. All right. Any questions on that? Oh, it's not your bad, Nick. That's all right. Either way is fine. You know, they're equivalent. So you just plus or minus one. Okay. All right. So maintaining the heap property. What if the priority of an item increases? We need to fix the heap, right? So if a priority increases, then we know that it has the potential to move up the heap. So we're going to call fix up, which is something that you will implement. We're going to basically you just swap the node that has been changed with its parent if the priority has increased greater than its parent. And you keep doing that until you reach a node that if you swap, the heap property would not be maintained. Okay, so can anyone tell me what the complexity of fix up is? Think about like, we have our, maybe I'll go even one farther. Right, we have this. Let's say we change one of these. You know, we change this one. How many nodes are we going to possibly look at? Right, Nick says log n. Good answer, Nick. And that's because, you know, we're only going to have to compare with this one and this one and that one, right? There's no other like possible nodes that we would compare with. And so we know it's a binary tree. Well, we know it's a tree and we're guaranteed completeness. So we know that this is going to be, you know, at most we're doing log n comparisons. Okay, good stuff. Any questions? Okay, we'll keep going. Yep, number of levels in the heap, which is always log n. Okay, what if the priority decreases? Is the inverse problem, right? So we have a node anywhere in the heap, and the priority is going down, so we just have to call fix down on it. And clearly, this is also going to be O of log n, because you could start at the root and go down to the leaf, right? Okay. Great. All right. So heap insertion, another thing that you'll be doing on the project. So what we can do is, let's say we already have a heap, and we're gonna insert this last node over here. We're inserting this one. So we can just put it here, and then we can call fix up to figure out where it should properly go in the heap. So not bad. And we can imagine that, of course, this is also going to be O of log n because we're just calling fix up on the bottom of the tree. Okay. Heap removal. How do we remove an element from the heap? We're going to switch it with the last element, delete the last element, and then call fix down on the element that's in the root position. So I will have drawn this tree so many times by the time this lab is over. Okay, let's say we have this. All right, and now we're gonna switch the last one with the first one. So we get that, and then we get these, and then we get 1, 2, 3, and then finally this one, right? We pop that out, and then we just figure out where that purple node ends up in the tree. So then once we're done, it'll look, maybe it'll look something like this, and then this, something like that, right? The purple could switch in here. It could switch with either of these two, depending on which one has the low higher priority. Okay. All right, consider an empty max priority queue. If we insert the elements 14, 4, 5, 23, 9, 11, 2 into the heap, and then we remove the most extreme element twice, what are possible array representations of the heap? All right, so let's start by inserting the elements. Do you want to try this, or do you want me to just go ahead and show you how to do it? This is like straight out of the exam. Go ahead. Okay, I'll just do it. All right, so our heap begins with 14. And then 4, no problem. We'll just put that, it's a max heap, so we want 14 on top still. 5, okay, great. All right, now 23. So we're gonna put 23 at the bottom. And we're going to compare it with 4, and those two switch. And then we're going to compare it with 14, and those two switch as well. Okay, now we've finished the fix up, so we can continue with inserting elements. We're going to put in 9. Looks good. 11. Okay, we're going to have to switch these two. And then 2. Okay, so this is our final tree after all the insertions. Now we're going to remove the most extreme element twice, right? So 23 is the first one that goes. So 2 will be at the top, 14, 11, 4, 9, 5. Okay, we can get rid of this one. All right. Now we're just going to do some switching. 14 is higher priority, so we're going to switch that. And then 9 is higher priority than 2, so we're going to switch that as well. Okay, we're all good again. So now we can do our second pop. We're going to take 5, put it on top. 9, 11, 4, 2. Get rid of this. Okay. And now 5 is going to switch with 11. Oop. And that's our final tree. So then to make that an array, we can just do 11, 9, 5, 4, 2. 4, 2, which is D. Does that make sense to everybody? I'm not writing the heap questions this semester, but I have in last semester's. Actually,
Can you draw the original heap again?
Yeah. Like go through the process of insertion?
Yeah.
Okay. Okay, so we start with 14. Right, just insert 14. There's nothing in the tree, so it'll always go through it. 4, Now it's a max priority queue, so we compare 4 to 14 and we're good, right? So every time we insert, we call fix up no matter what. But in this case, 4 doesn't switch with 14, so we're done. Okay, 5, call fix up, we're still good. Okay, we're gonna insert 23. Remember, this is a complete tree, so we're always filling out left to right. So we're gonna insert 23, we're gonna call fix up. Clearly 23 is higher priority than 4, so we're gonna switch those two. And 23 is also higher priority than 14, so we're gonna switch those two. Okay, now we've called fix up on 23. That operation is completed. So now we can insert our next element, which is 9. So 9. Let's call fix up on 9. 14 is greater priority, so we don't move it. 11. Okay, call fix up on 11. 11 is greater than 5, so we're going to switch those. And finally, and then 11 is less than 23, so 11 will stay where it is. And then finally, we're going to insert 2. 2 is less than 11, so it will stay where it is. Does that make sense, Julia?
Yep.
Great. Okay. Yeah. So it's good to be able to know how to assemble this. All right. We got the right one. Okay. All right. So we're going to talk a bit about heapify. We start with an empty heap and we insert items one by one into the heap. The complexity of this method, as we talked about a few minutes ago, n log n, because for each of n elements, we are doing a log n operation, which is fix up. So it's n log n. All right, there's an explanation. Okay, idea number 2. So we take the underlying array to be the unsorted array. And then we'll go through a couple different ways that we could do this. Method 1 is called fix up, starting from the top of the array and moving down. And method 2 is fix down, starting from the bottom and moving up. So we'll talk about each of those. All right, spoiler alert, number 2 is better. All right, so fix up. The idea is that we're going to fix up starting from the top and moving down. So the complexity of fixing the position of an item is, in this case, the depth of the item, because we're going up. And we need to fix every item. So here we're just looking at the depth and the number of nodes that can be at that depth. So then we get a summation of terms, which ends up being clearly the largest number in this the largest term in this summation will be n over 2 times log of n, which is true because the max number of nodes at the maximum depth is n over 2. If we imagine that we had nodes here with arbitrary elements, then we can see that 1, 2, 3, 4, 5, 6, 7, 8 nodes are on the bottom. 1, 2, 3, 4, 5, 6, 7 are not on the bottom. So it's about n over 2. And okay, yeah, so I guess n over 2 plus 1 would be the max. And then yeah, we can also see this because the tree is logarithmic, right? So we're always going to have up to n over 2 nodes on the bottom. Okay. So this is n log n. Okay, so now we can call fix down, starting at the bottom and going to the top. So the complexity of fixing the position of a single item is the height of that item now because we're going down. And we need to fix everything to make sure it's in the right spot. So at height log of n, there's one node now, which is the key here. And at height 0, or height 1, whatever you want to call these nodes, we have n over 2. And so that summation comes out. Oops, sorry. And we get this term as the biggest one. Or no, not as the biggest one. I'm sorry, as the final term. And then, we can pull the n out of the summation. And then we know that this series from analysis will sum to 2. So we get n times 2, which means that this whole thing is O of n, which is better. Okay, so Heapify, very efficient. It's a great thing. Make sure whenever you're thinking about, I need to use a heap for this unsorted data, typically it's implemented as a range-based constructor, or you can use, sometimes there'll be like .heapify or whatever, and you'll be able to heapify an array explicitly. So whenever you're thinking about heaps, think about the fact that we can use heapify instead of just like throwing stuff into a heap, and you need to make sure that that's what's happening. Okay, so here's an example of heapify. There's some animated slides we'll go through. All right, so we're going to start at 5. 5 is in the right position, no problem. Okay, so 5 is fixed. We're going to do 3. Now 3 is fixed, 13. Right, so there's going to be n over 2 of these nodes that don't need to be fixed, like guaranteed, like no comparisons, right? Because they're at the bottom, there's no place to go. Okay, so 40, also good because we're creating a max heap. Okay, so 1, we're gonna have to switch and we compare it against its 2 children. Obviously 13 is greater than 3, so 13 will move up and 1 will move down. Okay, looking good. All right, so 16, 27 is greater, right? So it will move up. Now that's locked in. So you can see as we're going, like this is a subheap, that's a subheap, and that's a subheap already, right? So we're joining these heaps together to be a single heap. We are the unifying of the heaps. Okay, so 24, we're going to switch with 40, and then we're not going to switch that with 5. And then finally, 3 will be switched with 40 as well. 3 will then be compared against 13 and 24. 24 is bigger, so it'll go. And then it'll also switch with 5. Right, so that was like the full log n movement for 3. Okay, and now all of a sudden we have this big heap that is a true heap, and it's the full data structure. So we're happy. That is how Heapify works. Okay, so we're calling fix down, starting from the bottom. The complexity is O of n because n over 2 nodes have 0 comparisons, right? Or 1 comparison. Basically just checking that there are no nodes underneath it. Okay, calling fix up has complexity n log n, not great. In your project, this function is called update priorities, and all you have to do is call fix down, starting from, you don't even have to start from the bottom in your project. It will be, you'll do better on the tests if you start at, oh, that's not the right thing. Start at and over to +1, I think, to guarantee that you hit all the nodes with children. Okay. And that is how you get on the leaderboard, or at least pass the test cases. So, okay. We're gonna move on. Right. So heap sort just uses a binary heap to sort items. You're gonna use heapify, and then you're just gonna pop everything out of the heap, right? Because in a heap, it's not sorted. It's just ordered in a specific way so that we always know where the largest element is of any subheap. So we heapify for O of n, and then for all n elements, we just pop it out, and that is our sorted array. So that final process is n log n, because for n elements, we're doing log n. It would be fixed downs, because with removal, you like swap the two, switch and swap. You swap the two and you call fixed down on the root. So you get O of n plus n log n, which is n log n. So sorting is still n log n. The leaderboard, sorry, I didn't mean to bring that up. I actually hate the leaderboard and have been trying to get it removed from the autograder for all 6 semesters that I've worked. But if you want to look at it, if you go to any of your projects or labs and you see the name of the project or lab, and then right next to it, there's a little trophy. You can click on the trophy. It's like the top 10 submissions in runtime. Check it out. Okay, heap sort. Here we have a unsorted array. And the first thing we're gonna do is heapify. So make it into a heap. And then now we have a heap. So then we're gonna start swapping elements, and then we're gonna pop 89 out of the tree, but it's still gonna be in the array because we're trying to have a sorted array. But now the tree ends here instead of at the end, right? So this is just the same process for all of these, right? We're fixing places in the array, and we're maintaining the heap property in between. Okay. That was maybe something important. Okay. All right. So now we have a sorted array, and we're done. Okay, any questions on heaps, heapify, anything related? I'm breezing past heap sort because I feel like once you know what heapify is, then it's just all you're doing is popping out of the heap. Okay, I'm going to keep going. If you have questions, just post, and I'm happy to go back. All right, we're going to talk a bit about sets and union find, which is usually referred to as a data structure in this class, but it's not a data structure. It is an algorithm. So sets are collections of objects. There's only one thing you do with a set, and that is check membership. All of these things are the same set because set elements are unique. These are things that you probably know from 203 or linear algebra if you've taken it, or analysis if you've taken it. Yeah, no duplicate elements in a set. All you do is check for membership. That's all you need. Okay, the empty set is a thing that we want sometimes, and it's represented with that. Okay, we can do operations on sets. Union is the union of two sets. You are taking elements from set A and set B and putting them together in a new set. And obviously all the elements are distinct because the new set is still a set. So the union is someone is whiskey in my house. Yeah, I'm sorry. Yeah, I think there's some breakfast being made behind me. I'm on the West Coast right now, so it's like 9 a.m. Okay, so yeah, I'm sorry if it's distracting. If it gets too much, just let me know and I will move somewhere. So union is classic. Got to draw the Venn diagrams for set operations. So let's call it union purple. Union is everything, right? Intersection is just the overlapping elements. So that's here in the middle. And set difference, A minus B, which we'll just use as A minus B here. When we get, let's try this blue. Set difference will be everything over here that's not in the intersection, right? And let's call this A, and this is B. Okay, so I think that this should be something that this should be review material. If it's not, I think that, for this class, thinking about the Venn diagrams is more than enough. We're not going to ask you to be doing like set proofs or set problems on the exam. The most that you'll have to do is describe union find. So, or like some union find problem. So as long as you understand union find, I wouldn't worry about sets. Okay. A is 1, 2, 3. B is 1, 3, 5. What is the union? Any thoughts? Do we have them sorted? Doesn't matter if they're sorted. Right, it can be in any order. It's still a set. Okay, Sam says 1, 2, 3, 5. Yep, so my thought is like, I'm gonna go through A, add everything in A, 2, 3. And then I'm gonna look at B. 1 is already in there, 3 is already in there. Okay, 5 isn't in there, 5. So that's A union B. Okay, how about A intersection B? One and 3. Yep. So, you look at each element in A and you see if it's in B. 2 is not in B. 3 is in B. Okay. That's what you got to do. All right. A minus B. So all the elements of A that are not in B, only 2. Exactly. Okay. Great. Y'all are good at sets. That's pretty much all you need to know. All right. We did it. Okay. A sorted vector is one good way to implement a set. You can use binary search to implement membership, and that's log n, so that's pretty good. For a set that needs to insert or erase elements, often things like AVL trees, which we'll talk about in maybe a month, hash tables, which we'll also talk about in a few weeks right after the midterm. These are great things for sets, and they allow you to do insert, erase, and membership checking very efficient. Okay. I'm going to leave the implementation of union, intersection, and set difference to you all. Just think about it. It's a good test question. I don't know if me going over it is super beneficial because I don't think it matters too much. like we're not going to ask you set questions beyond union find on an exam. Okay, here are the answers if you want to know them. Here's a few other things that you really don't need to worry about on sets. Symmetric difference is any object that is in either A or B, but not both, right? So symmetric difference is this and that. Cartesian product is the cross product of the elements. Oh my gosh, now the dog is popping off. Cartesian product is the matching every element with every other element. And then the power set is a set whose members are all the possible subsets of the original set. So here are the answers to those final two questions. Don't have to worry about cardinality. We're not asking about it. You can reason about these things on your own, but don't worry about it. Okay. Okay, we'll just do these real quick. That's not what I wanted. But I don't know, like having this stuff in the lab, I think is questionable because it doesn't matter to the class. So A minus B, it's going to be 2 and 5 because those are the only elements that are in strictly one of the sets. A cross B equals. So 1, 1, 1, 3, 1, 5, 2, 1, 2, 3, 2, 5. 3, 1, 3, 3, and 3, 5. So it's kind of up to your implementation of set whether, for example, 3, 1 and 1, 3 are the same thing or not. They could be, they could not be. It's up to you. Kind of depends on what you want to call like an element of your set. Okay, and then the power set of A is a set who begins with the empty set. Here's one subset. Here's another subset. Here's a third subset. And then you get the pairs, 1, 2, 1, 3, and 2, 3. Whoa, I'm getting real loose with the curly braces, I'm sorry. Okay, and then you have obviously the full set. Okay, good. Yeah, so it looks like here we are saying that 1, 3, and 3, 1 are both in it, but they don't need to be. Okay, how do we know if two things are in the same set? Are A and B in the same group? How we find that out? This is find. And now if we combine these two sets into a single set, are they now in the same group? Clearly, yes. So union find is a data structure or algorithm. It kind of depends on like what exactly you're doing it and how you implement it, But all it does is manage disjoint sets, and it's the operations that you want to do on it are union and find, right? So either you can combine sets or you can tell what the membership of any item is. Okay. So how do we tell if two people are citizens of the same country? One thought would be, if we're working with him, them, her, whoever, then we can just check who the ultimate representative of that person is, right? And then if the other person that we're dealing with is over here, then all we have to do is check here and there. And so then we'd be able to see that they are not of the same country. So check if they have the same leader. Okay, and all you have to do is walk up the representation path until you get to the leader. So for example, you could go that way. And then, this is us checking like what is the membership of any element in any group. Okay, so how do we combine the two groups? Let's say, US and Canada. Okay, looks like the US has has overtaken Canada. And now everyone is led by Donald Trump, I guess. And this is like the operation of doing a union on these two sets. This is getting too political for me. Okay, so what we want to talk about is how we can make the find operation more efficient, because if I do this multiple times, right? Let's say that, in the US, our representation tree is huge. Like I'm represented by, people at the local, like the city level, the county level, the state level, and then the national level, and then there's like appeals courts and all this stuff. Like we have so many people that represent us. But if we do this one time, we walk the representation tree one time, then we can just update, if I say, I start with me in the US and I say, okay, who represents me? I go all the way up the tree. I find the president. I'm like, okay, so I'm represented by the president. Great. Now I can just say that I am represented by the president instead of I'm represented by my senator, who is represented by, or I'm represented by like my state senator, who's represented by the national senator, who's represented by the president. Now I can just say I'm represented by the president because that's the membership of the set that I care about. Okay. And that is called path compression. So it makes checking membership of sets easy in the future. Okay, here's a way to implement path compression, and that I believe is valid Python code, which is amazing. I mean, wow, so easy. Okay, so here is the without path compression. This is what finding the representative looks like in the tree. Now we've called find once and we want to compress that path. Okay, now we can just update that entire path to be represented by the final representative of the path. So that in the future, all of these searches become more efficient, but also all of these searches become more efficient. So path compression is a great thing. Okay. This is the final section here, and then I'll let you free on the handwritten problem. There's a little bit about pairs at the end, which we'll talk about very quickly. Okay, so union find using an array. The value at each index of the array is the representative of that vertex. So here we have 5 separate groups because at each index, the value is just the index. Right, so that's saying that the representative of each vertex in the graph is the vertex. Okay, so we can manage, we can create sets by saying at one index, the value is the index, a different index. And now we're saying that they are represented by something else. Okay. Now we have 4 is represented by 3. So you are represented by you. 3 is represented by 2. Right? And 2 is represented by 2. So now we know we're done at that point. Oh, just like the arrows I drew. Except probably they look a little nicer, I guess. Okay, so now it's kind of, we have to take this whole path to get to 2. Here's a way we can implement find. Okay, what is the worst case time complexity of find given a union find container with n elements? Think about, this example, right? What's the worst case? How many elements would I possibly have to go through to find the representative? Anybody? Sam says n. Yeah, exactly. We could just, this could continue. And then we would have the maximum is n. Okay, O of n, find 4 times O of n process. So now we can fix that through path compression. So as we go through, you can see we are updating the values until finally everything lies on 0. Okay. Oh, I'm sorry. This is not, we are not updating these values. This is how it looks before path compression. The first table, this table. And then the second table is how it looks after path compression. Everything, instead of this relationship, I'll just do this. Right. Instead of this relationship, we now just have that. Right. So very easy, very efficient. Okay. All right. Here is an implementation of find. So these are good things for you to go back and look at when you're studying for the exam. Just remind yourself of like how this would look in code. We're not going to ask you to implement union find, but it's certainly good to know how it can be implemented. And clearly this isn't, this is what, like 8 lines maybe. So it's not that hard. Or I shouldn't say that it's not that hard. It's not that long. So it's good to just be familiar with all the steps. I would understand like the pseudocode, so just understanding like what each step in this algorithm does. Okay. Okay, so without path compression, average time complexity of find is O of log n. So this is basically like probabilistic analysis of with a random sets. Then we can expect branching structure, and then we end up at log of some base of n. With path compression, then the complexity of find becomes an amortized O of alpha of n, which is the inverse Ackermann function, which you literally need to know exactly nothing about, not even the name. It's just like a fun thing to know. And we're trying to be somewhat precise here, so it's good to bring it up. Ackermann at like a billion evaluates to like 2.5. So it's pretty much constant time. All right. Or not Ackermann, inverse Ackermann. Okay. So it's better in both average and worst case. So we should use path compression. Okay. How are we going to handle union in this situation where we have two groups and we're gonna union this node with this node. But clearly what we're going to do is not union those two nodes. We're going to union the sets to which those nodes belong to, which means unioning the representatives of those sets. So now we do a find on both, and then we do the union on the representatives. In that find, we've done path compression, so this is now it's rendering our entire algorithm more efficient because we're doing path compression as we go. Okay, here's a way to go about that. Union is a reserved word in C++, so don't use that. But okay. Now, with path compression, union also becomes very efficient. So path compression is just a great thing to be doing in union find. Usually if we ask any questions on union find, it involves path compression. So be able to understand what that is. Okay. Here's a class that will do the set of operations for you. We already went over find and set union. And here's the constructor. And then we're done. There's a data structure. Okay, any questions on union find before we briefly go over pairs and then finish for the day?
Sorry, could you go over, like really briefly, just go over path compression again?
Yeah. So the idea, let's go back to the beginning here. This one will work. Okay, so the idea is when we do when we're checking the membership of any member of a set, we're going to have to find its representative, and then maybe that representative is represented by many levels of representation. So, here we have a few different levels. And the idea is that instead of every time we want to check the membership of that set, it's because, okay, so I guess here's what it comes down to is like, if we want to see if sorry, can't use two greens. If this person and this person are in the same set, then it is possible that, we could be like, what's the first representative? But it's much easier to just say, what's the ultimate representative of the two? If that person is the same, then we're done, right? So every time we check this membership quality, we have to go through on average, log n, a log n operation to find the representative of the set. So if we're checking membership a lot, it doesn't really make sense, particularly of the same elements, it doesn't really make sense to always be doing this log n operation when we could, instead of having the path point to here and then that path point to here and then that path point to here, we could just update all of these paths to point at the ultimate representative, which is the one that we actually care about. Oh my gosh, I'm just deleting everything. Sorry. Here. And so, and then we'd also be doing this here. This one would be pointing up there, and then this one would be pointing up here, right? So we're updating the representatives that each member is pointing at to make the find operation more efficient.
Thank you.
Does that make sense?
Mhm.
Okay. Great. It's kind of a confusing thing until you figure out why would I actually want to do this, or why do I care? But I think thinking about it in terms of this image, I think is helpful. Any other questions on union find, path compression, etc.? You know, this is obviously like the more abstract representation here. And here is like something that would actually be, this is like a really concrete implementation of this. Okay, if there are no more questions, we'll talk briefly about functors and pairs, and then we'll be done. Okay, functors, function objects, objects that can be called as if they were ordinary functions. You will use these in project 2. They're used very often because typically you have a custom data type that you want to compare against other instantiations of that data type, or even other data types, and you can do all of that with a functor. So basically you just overload operator parentheses, and then you've got a functor. So here we have a person, they have an age, and we have a comparator that overrides operator parentheses, takes 2 people, 2 persons, sounds wrong, and just compares their ages. So it just says it asks which is younger than the other. So this is something that you could pass into a priority queue, and then you would have a min heap. Because you basically swap when person 1 is less than person 2. Oogie. Let's do it. All right, like I said, you can put this in a priority queue. It'll work as you expect it to. And as long as operator less than is defined for an object of type T, we can have a priority queue of objects T. Let's see. Yeah, so here, like we define less than in the struct. So then in the priority queue, we don't have to define what the comparator will be, because it uses by default standard less for person, which is in fact this. Sorry, it's getting a little messy, but yeah. So that's a comparator. Any questions? Does that make sense? A comparator is, it's a way to have something in your code that represents a priority between different objects. So it is, obviously very important for this project, and actually for the rest of the projects, we'll be using comparators. But once you write one, I think it's pretty clear how to deal with them. Okay, a few slides on pairs and tuples. So a pair is a data type that it just takes, 2 things, you instantiate it with 2 types, and it's just a pair of, it is what it is, right? It's just a pair of objects. So there's not much more to say about it, really. It's basically a struct with 2 members, 2 templated members, first and second, and they're both you template the object, so you tell the struct what the type of those members are. So here's pair with a string and an int, ex281. Standard make pair does it will create the pair for you. You can also use this constructor, and you can also use the assignment operator to construct it. Okay. To access elements, you can say dot first and dot second. You can modify, you can read. So that is that. And then two pairs are equal if and only if they have an identical first and second values. In the case of less than and greater than comparisons, pairs have default comparators that first compare the first elements, and then in case of a tie, compare the second elements. So this is important sometimes for the exam if there's a written question about pairs, but it's infrequent. But it's good to understand this behavior. The exam question obviously would not rely on this information because it's very like niche, esoteric, but it's a good thing to know that you can use this. Okay, tuples are pairs except arbitrary length. So here's a tuple of 4 objects. It's the same thing. It works all the same ways except it's arbitrary length. And then you have to use this kind of ugly like get function to get things out of it. Unfortunately, because there's not, there's no limit of the number of things that can be in there. You can concatenate them using tuple cat. It's kind of a cute name, I feel. Okay. And then you end up with like this crazy thing, which at some point you got to figure like, what am I actually using this for? Should I use a vector or a struct instead? A struct is nice because you can name things. But a tuple, sometimes you need it. Okay, there's a handwritten problem. I'm going to let you all do that. And in the last couple of minutes here, I'm just going to talk about project 2 a little bit. I'll just keep that up. For project 2, well, first, does anyone have any questions on pairs or tuples? I kind of flew through that, but to me, this seems like something you can go back to. It's mostly like dealing with like syntax and stuff. And if you feel like you want pairs or tuples, then I would just look at these slides later. Okay, for project 2, there's a part A and a part B. Part B is part A is like making a driver, and there's this whole like program that you have to deal with. And then part B is just implementing priority queues, different implementations of them. My suggestion would be for part B, do the sorted priority queue first. You can do it in like 4 or 5 lines of code. It's very short. It's very simple. It's just a sorted array. All you have to do is keep it sorted. So I would do that first. You kind of get an idea for like what a priority queue is, how it's supposed to act, what the different options on the interface mean. And then I would go and do part A, start figuring out like how things work there. And then when you get stuck, come back to part B, do the binary heap first, and then pairing heap is the last one that I would do. It's the most complex. Usually we make kind of a big deal about it on staff. It's not that horrible. It's just pointers. You just have to deal with pointers. And it's frustrating, but there's 3 functions that are basically the problem. And once you figure out one of them, you've basically figured out all 3. But that's the one I would approach last, because you want a pretty firm understanding of like exactly how a priority queue is supposed to work at that point. What else would I say? Oh, most of the binary heap stuff is in the slides between lab and lecture. And then for pairing priority queue, there's 2 papers. One of them, I think Sani, I believe, is great, and you should use that and reference it for the project. And the other one, you should just ignore and don't read it. But yeah. All right, that's all I have to say. I'm going to go ahead and stop the recording.